Hello, we are in our last section for chapter 11. We are in section 11, chapter 11, section 7, and we are finding the areas and volumes of similar solids. So let's jump in and talk about what similar solids are. These are solids that are the same shape. Solids that are the same shape, but different sizes. And all corresponding dimensions are proportional. Now, we've done something similar to this section in our area chapter as well. So some of these proportions, they might sound familiar to you because it does relate. So first of all, we're going to have three different types of ratios, okay? We're going to have a similarity ratio, a surface area ratio, and a volume ratio. Now, I'm going to give you kind of like a formula for these. So let's just pretend that we have two similar solids, and it doesn't have to be a cube, but it might be. So a cube is just one scenario, okay? So a cube is just the simple way to do this. Let's say that this has a side A and this has a side length B. For the similarity ratio, it's just A over B. For the area ratio, you are going to square those values. So it's literally A squared over B squared. Now remember, a ratio is not necessarily the actual value of the areas. It is a comparison of the areas. So ratio is not always going to tell you the specific literal length of something or the specific literal area of something. It's just going to tell you how it compares to something else, okay? And then we have the volume ratio, which is A cubed over B cubed. So ideally, if you start with the similarity, then you can square it to figure out area, or you can cube it to find volume. If you start with volume, then you would cube root it to get to similarity and then use that in order to get you up to area. So let's just take this one piece at a time. First, with determining if solids are or are not similar. So in this first question, it says, are the two solids similar? If so, give the similarity ratio. What we're going to do, we are going to look at corresponding measurements. So notice the height of this one is 5, the height of this one is 15. We're going to compare those. 5 over 15, and we're going to reduce that. That reduces to 1/3. Okay. Then we're also going to compare their radiuses. So this one is 3, this one is 9. We're going to put it in a fraction. 3 over 9. What does 3 over 9 reduce to? 1/3. And we're asking ourselves, okay, do these numbers get us the same results? If it is the same result, then they are going to be similar. If it's not the same result, then they're not going to be similar because that means they're not proportional. They did not keep a consistent ratio. But because these are both 1/3, they're staying the same, we're going to say, yes, they are similar. And what's really handy about this strategy is, what's our scale factor? Our scale factor is that reduced ratio of 1/3. In other words, this small one is 1/3 the size of this one, or the big one is 3 times bigger than the small one. It's according to kind of what direction you go in the problem for how you're looking at it. All right. So in our next examples, it says calculating similarity, area, and volume ratios. So in example A, it says find the similarity ratio and volume ratio of two similar cylinders with surface areas of 98 pi square feet and 2 pi square feet. Now, here's the thing. We know we're working with similar cylinders. They're telling us right here. We know that they are similar. And their ratio right now is 98 pi over 2 pi because those are the two values that we were given. And this is for area, for surface area. For right now, we would like to just ignore the pi because it's not helping us, and we can just reduce them, because if pi is on top and bottom of a fraction, we can just reduce it and basically they cancel each other out. Now we have 98 over 2. And when you are working with ratios, you want to reduce them as much as possible. So 98 over 2, both of those are even, all right? So I need to write this in pen, sorry. So 98 over 2, both of those are even. If we divide both of these numbers by 2, then we are going to get 49 over 1. 98 divided by 2 is 49. 2 divided by 2 is 1. So the area ratios now, based off of the values that we were given, we just put them in a fraction and reduced it. The area ratio is 49 over 1. And I'm just going to write in the corners what these ratios are. So we've got a squared over b squared, a over b, and a cubed over b cubed. My suggestion would be, if you do not have the similarity ratio and you need to figure out something else, get to the similarity ratio first and then figure out anything else. So notice how with our formulas, the surface area are these numbers squared. But for similarity ratio, it's just the numbers plain. So in order to get from area to similarity, we need to take these numbers and square root them, okay? So we are literally gonna take 49 over 1 and square root them. So I'll just do that work right here in this box. So 49 square rooted over 1 square rooted is going to get us 7 over 1, because the square root of 49 is 7, square root of 1 is 1. 7 over 1 is the similarity ratio now, okay? Because it's a over b. But surface area is a squared over b squared. Well, since we started with that and the ratio is squared, we got to square root it to get to a over b. But now, the reason I suggest getting the similarity is because we can easily figure out the volume ratio now, because all we have to do is take this a over b and cube the numbers in order to get the a cubed over b cubed. So a is 7 and b is 1. We're literally just going to say 7 cubed over 1 cubed. And when we put that in our calculators, because I do not know what 7 cubed is, that's 343. And 1 cubed is 1 times 1 times 1, or 1. So that's my ratio for every single one. According to where you are, it's going to determine, are you going to cube root it, are you going to square root it, or are you going to square it, or are you going to cube it? If you're going this direction, like left to right, you're going to square it to get to here and cube it to get to here. But if you're going backwards, to get from volume to similarity, you have to cube root. To get to area to similarity, you have to square root. So it's kind of like working a problem forwards or backwards based off of the information you're given. Let's do it one more time in this example, just so you can see it again. So here it says, find the similarity ratio and area ratio of the two cubes. So what we've got going on, are we given the two volumes? So when we write this ratio out, we know it needs to be in the volume box. I'm going to put 729 over 1,331. And as far as I'm aware, these cannot be reduced. So if we're looking at our basic forms, volume ratio is a cubed over b cubed. Area ratio is a squared over b squared. Similarity ratio is a over b. My suggestion, if you do not have similarity, solve for it first. Because we're going right to left, we need to cube root these numbers in order to figure out the similarity ratio. So we're going to have to use our calculators. So what we're going to do, we're going to type a 3 and then the second button, and we're going to type this button right here because the symbol above it has that little X in the radical symbol, and now this means cube root. And we're going to put this number, 729, into that calculator. When we do that, we get a 9. So the cube root of 729 is 9. So that's going to be our A value. Now we're going to do the same thing for the bottom of the fraction. What is the cube root of 1,331? So let's type that. So we're going to say the cube root of 1,331. That's getting us 11. Okay. 9 over 11 cannot reduce, so this is perfect. 9 over 11 is our similarity ratio. This is our volume ratio. But now that we have the similarity ratio, it's a lot easier to figure out area ratio, which is why I always suggest if you don't have similarity, find this one first. I'm going to write this down actually. Find this one first. Usually, because I mean, I'm sure there's an exception to every rule, but it's great to start with this because this is kind of like your foundational piece, okay? So now to get from a over b to a squared over b squared, all we have to do is take our numbers and square them. So we're going to take 9 squared, which is 81, and then 11 squared to get us 121. And then there is your ratio for your surface areas. Awesome. So that's how you find the ratios when you're given ratios for like a different form of measurement. Like if you're given volume, you can find the ratio for similarity and area. Now, we can also apply that to find specific values in word problems. So that's what we're going to do in the next example. So using similarity to calculate surface area and volume area, and volume. So in this first example, we've got 2 similar paint cans, and it says the lateral areas of 2 similar paint cans are, oh, there is a typo here. This 6 should not be there, are 1,019 square centimeters and 425 square centimeters. The volume of the smaller can is 1,157 cubic centimeters. What is the volume of the larger can? Okay. Here's what we need to do. We need to know what we're starting with. So notice we are starting with areas. And we are given this value and this value for our areas. So our area ratio is going to be 1,019 over 425. As far as I'm aware, this does not reduce. We are going to try to calculate volume. In order to calculate volume, you have to have volume ratios. So I'm actually going to write that out too, because that's pretty important. To calculate volume, you need volume ratios. But here's the thing. The only way you can get a volume ratio is by first finding the similarity ratio. So what we're going to do is the strategy that we did up here. Right now we have area ratio. We're going to square root to get similarity ratio, okay? So I'm literally going to find similarity ratio by square rooting these. So 1,019, 425. Now when we put these in our calculators, we are going to get some messy numbers. I'm just going to round to the nearest tenths place. So 31.9 over 20.6. Okay, now this is a rough estimation because we can only do so much when we got messy numbers. So this is our similarity ratio. Okay. Now what we're going to do is take these numbers and cube them to get our volume ratio. We have to get volume ratio because we're trying to calculate volume in the problem. So we're going to take 31.9 and cube it and 20.6 and cube it. So 31.9 cubed is 32,461. 0.8 basically. And then 20.6 cubed is 8,741.8. Awesome. Now we have a volume ratio, and this value right here is what we're going to use to set up a proportion. So we did all of this work just so we could figure out volume ratio, so then we can set up a proportion. So right now, this is the proportion of the big volume over little volume. So let's write that out over here to the side. So we've got 32,461.8 over 8,741.8. Now notice this is the big value over the small value. And I know that because this is a bigger number and this is a smaller number, okay? So this is the ratio for the volume of the big paint can, and this is the ratio for the small paint can. But we're told explicitly the volume of the smaller one is 1,157. So when I set up my proportion, because small is on bottom, I'm going to put this 1,157 on bottom, and my variable is going on top. Now we have a proportion. You've done this 1,000 times in my class at this point. You guys know how to solve proportions. You cross multiply. So let's do this. We are going to get 8,741.8 times x is equal to this stuff multiplied. So give me a second for that because that's a bit to type. 32,461.8 times 1,157. That is getting me quite the number. Okay, let me write this down. 375,583.02. Okay, 37,558,302.6. I could put that in there, why not? Okay, now what we're gonna do, get that x isolated, we're gonna divide by 8,741.8. And we are getting 4,296.4. This one was without a doubt a tedious problem. Next problem will be a little bit neater, I will say. I'd say both of these next ones are, but we're gonna do it again. So if that was tough, we're doing it one more time to help you out, or two more times actually. So here it says similar pyramids have volumes, so notice we're starting with volumes of 48 cubic centimeters and 162 cubic centimeters. The surface area of the larger pyramid is 135 square centimeters. What's the surface area of the smaller one? Okay. We are starting with volume, but we need area. So once again, to calculate area, you need the area ratio, but we are given volume ratio. That's what we started off with. So volume ratio is 48 over 162. Here's the thing. Those can be reduced. I can see that they're both even numbers. So if I reduce them both by 2, that will get us 24 over 81. But then I can see both of those can be reduced by 3. So when I take 24 divided by 3, I'm getting 8. And 81 divided by 3 is 27. Okay. This is reduced as far as possible. So this right here is my volume ratio. Volume ratio right here. We need similarity ratio next. Because it's best to go that similarity ratio first if you do not have it. So to get from volume to similarity, we are going to cube root these numbers. Now these are smaller, so you might know the cube root of 8, but if not, you can go to your calculator. You're gonna type a 3, hit the second button, and then right here, and then type in 8, and you're gonna get 2 as the cube root of 8. So for similarity ratio, we're gonna get 2 over, and then the cube root of 27 is actually 3, so I just know that. So the similarity ratio is 2/3. Now we're going to use the similarity ratio to find the surface area ratio. So the area ratio, we're going to take 2 and square it and 3 and square it to get it 4/9. Now, the reason I'm doing that is because of this concept right here. We've got A over B for similarity, A squared over B squared for area, A cubed over B cubed for volume. We had to get area because that's what we're trying to calculate in our problem. Now we have the area ratio. We're ready to set up our proportion. We're going to solve. So we have 4/9 is equal to, now notice how 4 is the small one and 9 is the big one. When we set up our second proportion, we need to put small over big because that's how we started this out, or that's how I did. So here it says the surface area of the larger pyramid is 135. Because 135 corresponds with the big one, it's got to go on the bottom, and x is the variable. Okay, we've got our proportion. We cross multiply, so it's going to be 9x is equal to 540. Divide both sides by 9, and that gets us 60. So the surface area is going to be 60 square centimeters for that one. All right, we've just got one more word problem. And fortunately for us, we were given the similarity ratio. So it says 2 similar boxes of detergent have heights of 6 and 8. Well, that is a one dimension, that is a similarity ratio. So similarity is 6/8, but we can reduce that to 3/4. This is our similarity ratio. But then it tells us that the smaller box contains 52 ounces. How much detergent does the larger box? So this is actually a volume problem. We need to figure out the volume ratio. So we're going to go to volume ratio by cubing these numbers. So right now we have similarity. We have A over B. To get to volume, we cube it to get our volume ratio. So 3 cubed is 27. 4 cubed, I don't know that one, is 64. And notice okay, so this is our volume ratio. Now we're ready to set up our proportion. So we have 27/64, and this is our small over big. That's just how I set it up. So now we're going with it. Because there's lots of ways you can set up proportions. You just got to keep it consistent. It says the smaller box contains 52 ounces. This 52 corresponds with the smaller box. So now when I set up my second fraction, this 52 is going to go on top because I've said the small numbers are going on top. And the variable is going to go on bottom. We have our proportion. We're going to cross multiply. So I have 27x is equal to 52 times 64, which is 3,328. Isolate the x by dividing by 27 on both sides. And I get 123.3. All right. So with that being said, that is the end of chapter 11. I hope these notes have been helpful for you. And of course, as always, please ask me if you have questions. I am here to help. Please have a wonderful night.